All right. Thank you all for joining. As Boris mentioned, I'm going to be talking about cooperative ground and common ground in cooperative communication. This is work that appeared in NeurIPS last year. And again, as Boris mentioned before, I have a similar story to tell, which is that this is joint work with Xiaoran, who's a graduate student who since graduated, and Yash, who's a postdoc who's still working with me, fantastic postdoc, working with me. And so all of the parts that you like, you should attribute to them, and if there's anything you don't like, you should attribute to me. 99.73%, I think, is the number. Anyway, so yeah, I'll be talking about common ground in cooperative communication. So this is a little bit different than the things that you've seen so far, but I think, hopefully you'll get the sort of spirit of where we're going and where the connections are once we get started here. So I'll start from, the sort of 10,000-foot view, which is to say that somehow the communication of the kind that we do right now is magic, right? I'm sending you vibrations through the air. You're experiencing these as words that have meaning, semantics, right? I can compose them in structured ways. We call this syntax. And you'll interpret them situationally. So what I say depends on context in interesting ways. And we call this whole ensemble language. Right, and it is truly stunning that it works at all, right? Sound waves all of a sudden become, ideas. And we do all of this, perhaps most surprisingly, without really understanding what each other knows, right? So I have some broad stroke sense of what you know, given that we've sat through similar lectures over the past couple days. But all of you bring to bear much greater experience that I have no insight into. Nevertheless, I'm going to try to compose 50 minutes worth of talking that will hopefully have you leaving the room with some new insights about the world. And this problem in which we don't quite know what each other knows is called the problem of common ground. That is what is sort of shared between us. And this arguably is the point of language. If we both had the same knowledge and knew exactly what each other knew, then what really would be the point of communicating, right? We have to sort of go beyond what each of us know somehow to communicate new substance to each other. And that's really what language is here for, in some sense. We capitalize on everyone else's experience to learn things indirectly. So that's the human side of the world. Of course, as we all know, there are amazing advances in modeling language, right? And the idea here is we're going to generate plausible completions, probable completions even, given training on huge amounts of text data. So just analyzing the statistics of what people have written down over the centuries. It's a little unclear in what sense communication here is implemented. Right? We have the statistics, somehow we have some, at least weak notion of meaning in here, right? We also have the ability to sort of compose sensible sentences, so there's some notion of syntax, although not obviously explicit. But what is omitted is that there isn't really a notion of pragmatics, or at least not obviously so. And so, all of this leaves us wondering, well, in what sense have we, we've modeled language, but is it really a model of communication? And as a result, it's sort of unclear what these models are good for, right? Like we all wonder at the ability of these models to generate plausible text, but really, what are their strengths, right? And now there's a huge cottage industry in the world of machine learning and AI of publishing papers that enumerate these various strengths through all kinds of methods. It's also unclear, however, how to make them better. Right? What is it that they're missing? Well, we don't know. That's the whack-a-mole game that we're playing right now to try to figure out here are the interesting phenomena, here are the places where they fall down. And I think it's an interesting endeavor to sort of compare to humans, human language, in part because that's what these models are meant to be doing, is engage in some form of communication to understand how to make them better and also potentially make sense of human communication. All right. So I'll start with the game that I like to play. I'll apologize to the people who were here in the first week who will see this game for the second time and maybe others for the nth time. But it's a fun and simple game to give a sense of what really cooperative communication is. So this game that we're playing where we're mutually trying to understand each other's sound waves. And the game is insanely simple, right? We're gonna talk about two people, right? So now I'm drawing one person and a second person. And I'm gonna be able to say one of two words, hat or glasses. Oops, parentheses. So the game is you have to guess who I'm talking about, right? I'm gonna utter a word, you're gonna guess who I'm talking about, we're in this game together. And so I'm gonna say, watch out for the guy with the hat. The question is, who am I talking about? Nobody's voicing guesses, as people are sometimes. The one on the right? The one without the glasses, right? And so the logic here is that, of course we know that it's sort of evident in the situation that they both have hats, right? This guy has glasses and this guy does not, right? And so you can reason, well, if I meant to communicate about the guy on the left, I would have said the guy with the glasses. I didn't do so, right? I chose the ambiguous term, which must mean the other guy, because I had available this other choice. This is known, this is a phenomenon in linguistic pragmatics, known as implicature. There's a huge literature on it there, as well as in cognitive development, in robotics, in machine learning, right? It comes up in a variety of contexts, I think, to understand how two agents interact when both agents are intentional and know they're in a game together, trying to solve it. And we can instantiate this reasoning that I mentioned, right? So I said that you can reason about me. So if we think about me as the utterer, we'll call me the teacher for now. We don't necessarily mean education, but I'm gonna produce the data. You're gonna be a learner, so you're the person that sees the data and makes inferences. We can think about, well, I'm gonna have to make my board smaller because I'm gonna run out of space here, but if we look down the columns, we can think about, well, what it is if we were just randomly sampling, right? So there'd be a 1/2 chance of producing hat or glasses because they're both consistent with the person. This one, you would have to say hat because he doesn't have glasses. So that's the sort of teacher side, and you can think about the learner side after that, right? So on the learner side, we go in the other direction, right? So here we wind up, well, if he says glasses, he must mean the guy with the glasses, but if he says hat, and all I've done here is normalize, right? Make everything sum to 1, so you add up the values in the row and divide through by that, as you might expect. And we can play this recursive reasoning game. I can then go from the teacher's perspective and from the learner's perspective. But I think you can probably already guess where this is going to go, right? To where your guesses were, right? Which is that you should infer hat, even though it's ambiguous when I'm talking about, when I'm referring in this situation, right? And so this is the sense in which language is contextual. Right? The first part is semantics of the situation. The last part is how we're going to use it, right? And we can all agree on this. This is a sort of straightforward problem. So there are, as I said, loads of models of this. I'll talk a little bit about them later on. But in recent work, I will, let's see, what color shall I like here? We basically show that we can think about this problem. This problem is exactly equivalent to what's called entropic optimal transport. Hopefully you'll get an intuition over the course of the talk. So here it's discrete and finite, so we'll just think about discrete objects. So we have a cost, a plan, and then minus, sorry, I ran out of space. Whoops, we'll make this entropy of P, right? And so the cost here was the original semantics. The plan, P star, is the optimal plan that comes out. That's this plan right here, right? And so we can formulate this problem of cooperative communication as a problem of optimal transport. And I think that's interesting, right? Prior to this work, this is work that appeared in 2020, there was no coherent mathematical formulation. People had lots of algorithms for producing predictions about this, but no mathematical instantiation of like what actually the problem solved. But this is cooperative communication, at least in the sort of intuitive sense. And so if we were going to revisit sort of our desires here, we might ask questions that are sort of like this, like how do we scale these sort of very, very simple-minded, perhaps boring, if you've seen them many times from me, I've been doing this for many years, trait even, experimental examples to say like what do they imply for the actual use of language like we're doing in this room, right? All of these are very, very schematic, carefully constructed in order to give rise to the phenomena of interest. But it's also quite clear that when you're learning language, the situation is what you have, right? And so that kind of reasoning does matter. And so the question, potentially anyway, and the question that we'd want to answer is, do these ideas really matter? Like cognitive scientists and other folks have been thinking about these things for a long, long time, but like language models are here and they're doing really cool stuff. Like, do we have to care anymore? On the model side, I think there's an interesting question about what's the difference here between statistical regularities, right, next token prediction, which has gotten us very, very far, simple autoregression, and intentional action. Maybe there's none, but we need to be precise about, well, what is the intention doing, this kind of stuff, right? And the hope would be like maybe there'd be an interpretable, useful theory that might tell us how to make these models more powerful or tell us what we should do in order to get them to achieve all the phenomena that we want in a sort of nice and clean way. And so the idea here is like, can we shed light on the relationship between these two perspectives?
So can I ask that when you say statistical regularity, at least like in the kind of human language side, what exactly is random? Like the probabilities you assign to like what you think the other person means, that's kind of what's...
Oh, so here what I'm referring to is the language models themselves, right? They're just bootstrapping off the raw statistics, right? On the human side, it's, yeah, as you point out, a little bit less clear, right? So I've invoked a few other terms that might matter, like intentional, right? And so those might be subject to optimization processes like the story I just told. But yeah, on the language model side, right, it's really just looking at the statistics of what's happened. Yeah, any other questions? All right. So, and I'll reemphasize, what I'm going to talk about and feature most here is this problem of common ground, which is both totally central to language, but also totally omitted from the models that exist today. So this model that I pitched to you, this whole story hinges critically on the teacher and the learner knowing everything they need to know about each other. So if you're sort of thinking like a Bayesian, it would be, I need to know your priors, you need to know my priors, and we both need to agree on the mapping between words and states in reality. This is a heavyweight assumption, right? And arguably, it's a deflationary assumption, right? You've done away with the problem of language because I know everything I need to know about you already, and like that's really, that's it. We can solve the problem totally independently. And this is not unique to the framework that I put up. Literally every single one that I'm aware of does this sort of basic setup. So the question really is like, well, what is common ground? Can we relax this definition and do we get anything interesting? And then does it connect up to things that are closer to what we might think of as state-of-the-art AI instead of these simple little toy things? And as a confession ahead of time, I don't want to set anyone's expectations too high. We're not going to make it all the way to the state of the art, but we will make it some of the way. And I think what the portion of the way that will make it is interesting and evocative of what is the potential here. All right. So what is cooperative communication? We're going to think about agents. We're going to think about a teacher and a learner. I'm going to have in like sort of hinting at things, right? The teacher is going to be what we might think of as a decoder, right? They go from the hypothesis space to generate data. The learner is an encoder. They go from data to latent space. We're going to think about hypotheses and data. Data are the observable things. Hypotheses are the things that are in your head. We're going to have a marginal on hypotheses and a marginal on data, nu and mu, respectively. And what we're looking for here are communication plans on the H by D space that couples these marginals, right? And those are going to be the sort of pieces that we're looking for here. And what we need to do is say, well, what is common ground? Right? What does it mean to have common ground? And in particular, as a special case, this assumption that we had before of perfect common ground should be some special case of this general framework. Okay. So we start with a definition. I went from sort of fluffy and intuitive. Now we're going to just look at math for a while. Hopefully that works. So common ground is going to be a pair of sets of probability measures on D cross H. So we might think of pairs of sets of communication plans, right, from the teacher side and the learner side that live in the power sets of all possible communication plans. And this is going to represent the set of communication plans with the marginal nu, and this is going to represent the set of communication plans with the marginal mu, right? And so, as I said before, to sort of give you an intuition, in the original problem, we had priors on data, prior on hypotheses, and a mapping between the world that was assumed to be sort of known and fixed and shared. What we're doing is relaxing this, right? So we have two sets of plans, one for the teacher side and one for the learner side. And we're wrapping the priors into that, right? So this is indicating that it has this marginal or this marginal, right? So we have the teacher has their plans and their marginal, and the learner has their plans and their marginal. Right? That's the sort of idea here. All right. And so this is going to be common ground in general. It's the set of all choices that we might have. And we want to formulate an optimization problem that's like the one that I sort of showed you intuitively. That is, we want a pair of communication plans from the teacher's side and the learner's side that live in these sets that I mentioned. That is some way optimal, right? It's going to minimize this functional here. Where this functional is defined below. It has three pieces. This first piece is going to say, well, we should favor communication plans that are close together, right? We want teacher and learner's plans to be close together. That way they can communicate successfully. But we don't want to assume that they have to be the same thing, right? That was the assumption we had before. We have this term here, which is a divergence from the teacher's plan from what's known as the independent coupling. So this is analogous to an entropic term that I mentioned before. And then the third piece is that we want the teacher's induced marginal for the data, that left-hand side there, and the KL divergence, to be close to the learner's actual margin, right? And so you can see here, there's sort of three pieces, right? One is saying the plans should be close together, one is saying the marginals should be close together, and the other is an entropic regularization term.
Sorry, can I ask, so is mu-L just by definition always mu, but you're just writing it that way for clarity?
Yeah. So I wrote it there for clarity, right? So mu-L is mu, yes. But mu-T is the induced marginal on the teacher's side, right? So I put in both subscripts.
So similar like mu-T is nu,
Yep.
but again, you're just...
It's induced from the learner side, yep, exactly. So again, like your disclaimers, there's a little bit of notation here, and it's going to be not the easiest. Yeah.
Sorry, I lost track of something basic here. So IT, the teacher's plan, is like something like a joint distribution over both teacher and learner.
It's a joint distribution over data and hypotheses. Right? D cross H. Or joint measure. I should be careful here. Yeah. Okay. Any other questions? So let's meditate on this for just a moment. There's a couple things to note here. So perfect agreement between teacher and learner, right? Having the same plan is achievable if the intersection between these two sets is non-empty. So it's possible to achieve perfect agreement, but it's not required for the framework, right? So these two sets could have an empty intersection. And what you would be looking for is, again, plans, communication plans that are as close as you can get, given those sets.
Sorry, can I ask? So how can they have empty intersection? Isn't like new tensor mu always in there? Am I crazy?
Yes. So yeah, we'll talk about that. Yeah, good. Yes. So that's an excellent point. One of the features here that I didn't highlight, but was an innovation by Kantorovich in optimal transport, which is again sort of secretly what we're very close to here, is that there's always a solution in these sets, the independent coupling. Okay. So let's take a look at the bits here. I'll talk through them. Sorry, they're a little small. Okay. So this term here is going to be non-negative, right? It goes to 0 when teacher and learner have the same plan. Okay. This term is also going to be non-negative and vanishes when the marginals are the same, the teacher's induced marginal and the learner's actual marginal. When the first term is the same, the last term has to be the same as well, right? If you have the same plans, then you have the same marginals. And if both are satisfied, then we get a lower bound on the cost here. So our communication cost is going to be bounded by this entropic term. All right, so let's take a look at the parameters really quickly. All right. And we'll look at this epsilon parameter. So when epsilon is greater than 1, it's best to minimize the second term here. Right? So as epsilon is greater than 1, we want to make this term as small as possible. And in this case, we're favoring ignorance, right? So you have the same communication plan for all hypotheses. Right? And this is the independent coupling point, right? We're going to try to make this as close to 0 as possible. If epsilon is less than 1, the first and the third terms compete with the second. That is, we want to ask for as much information about each other as possible, right? So in the and then if epsilon equals 1, agreement is sufficient for an optimal solution, right? And this epsilon equals 1 has the feel of like probabilistic solution. Okay. So I've set this up purposefully rather general, right? So we talk about measures and we talk about sets of measures and these things. But now what we'd like to do, I mean, there are a variety of reasons why that's kind of nice, right? You get some mathematical cleanliness. But what we also want to be able to do is get to solutions, right? We want to be able to compute things, and we also want to draw lines to the world of machine learning and AI. And so what we're going to do is we're going to move from sort of a measure theoretic setup into the world where we have probability distributions. And we're going to call this the variational approximation, right? And so you can look at this problem and see that it basically looks the same, right? We're going to want couplings that live in a similar style set, right? Where we've introduced a little bit of notation here. The P sub g is the probability density function that approximates mu sub t, so on the teacher's side. Sorry, P sub theta, sorry. P sub lambda is the PDF approximating mu sub L, and F and G are going to be PDFs approximating nu and mu, respectively. And we'll set things up sort of as you might guess if you're doing Bayesian inference. That is, we want to think about the conditional distribution as being related to the joint and the prior. Okay. And so what we'll claim is that here is our variational formulation, right? And so we have an integral here over our data and hypotheses. We again have three terms, this term, and this term. They're roughly similar, right? In the sense that this is still our learners. Sorry, the gap between the marginal on here we got nu, and then we have a entropic term, and then here we have a slightly different term than we had before. But basically, you see that they're sort of roughly similar, right? And what I'll claim here, and we'll show in just a few minutes, sort of roughly, is that this is going to be interestingly related to encoder-decoder architectures, in particular variational autoencoders. All right. So again, these aren't quite the same. They're very close, but they're slightly different. And one can show through calculations that these aren't exactly the same. That sounded like it came from above. Very large ants got on top of the building. Someone brought food. What we can show is that these are very closely related, but they're not quite equivalent, right? And so I should say that here, what we're doing is we're looking at only the measures that have PDF approximations. So we're looking at a subset here. But we can see that they're equivalent up to an entropic term. And this is the cost of the approximation itself. I won't go through the calculation because it's not too enlightening, but we have it in the paper for if you're interested. So we've taken this sort of abstract setting, we've reduced it down into a variational approximation in more standard language. And what I'd like to do is try to make clear that this is, in fact, a particular form. It's not your standard variational autoencoder, but it's related to standard variational autoencoders, in particular by way of this paper that we had, might be 23. I might have put the wrong date. Anyway, Xiaoran and I had in ICML, in which we introduced what's called the coupled variational autoencoder. Okay, so this is just the formulation that we already saw, three terms. We see the three terms, everything's good. The coupled variational autoencoder also has three terms. And we can see that these are, in fact, of the same kind of form. The notation's a little different, so I apologize for that, but I brought it directly from the paper. We have two KL divergences, one here between marginals. So this, well, I'll come back to this in a second. This is an entropic regularization term, just like this one was. And then here we have a conditional and we have, let's say, an integral over a log term that we'll talk about. What's interesting here and different from previous variational autoencoders is this term at the end here, which is where the coupled term comes from, in coupled variational autoencoder. One of the issues with standard variational autoencoders is what's known as the prior hole problem. That is, your prior, if you generate from the prior, you can miss the data support, and you tend to produce noisy or not particularly nice samples. And so the coupling here is meant to resolve that problem, right? To enforce our approximate, our prior be close to our posterior be close to our prior. And so that was sort of the idea of introducing it. And we can be even more explicit and cache this out as a more standard formulation of the optimization problem. And so we can see here that we have an encoder optimization and a decoder optimization. And all we've done is cached everything out in expectations as one standardly does, right? So pausing for a brief moment here, what we've got to is that we've built a bridge from what we might think of as cooperative communication in sort of the cognitive science literature to variational autoencoders in machine learning. A quite explicit bridge, right? They're exactly equivalent in this particular problem of where we're establishing common ground. So what we'd like to move to now is to show that standard models that were out there before are indeed special cases. And again, I'll sort of like not be incredibly precise here in terms of mapping things out, but show you that the forms of these objects are very much correct.
Can I just ask for 1 second about this mapping? Mm-hmm. So suppose that there are more than two people that are trying to find, or more than two agents trying to find common ground. Is this like multi-marginal, like kind of optimal transport? So it just corresponds to some kind of like other autoencoder. I don't know if that's like a tensor autoencoder or something else.
It's a great question. I think it's not quite multi-marginal optimal transport. So for those that don't know, so optimal transport, right? Think of it in a discrete and finite case. You have a matrix and you have two marginals, right? You want a plan that sort of is close to your cost somehow, is one way to think about it. So if you introduce a third person, you might think there's sort of a third marginal, right? But the teacher and learner's marginals have pretty specific meaning, right? It's the priors and the data, right? So if you introduce a new learner, then they have a different prior. So far, so good. The teacher's data marginal hangs around, or one of the two anyway. So you could, in theory, set up the problem. But what you want is a single plan. You don't want a collection of plans, right? And that's the difference from
But where in all of this is there the asymmetry between the teacher and the learner?
Mm-hmm. Another good question. So the asymmetry between the teacher and learner is entirely implicit in the way the problem's formulated, which is interesting. So it's the teacher's responsibility. They know the true hypothesis, right? This is sort of by assumption. We didn't build that in, but I'll come back to that in a second. And they want to produce a plan that moves the learner's beliefs, right? So they have a certain responsibility. The learner also needs, they know their own beliefs, of course, but they also need to know the teacher's prior on data. But that's a relatively lightweight thing, right? You might think like, well, your beliefs are certainly more complicated than what costs in terms of utterances, right? Shorter utterances cost less, maybe, something, maybe a few extra terms, right? So there is an asymmetry, but there's things that both need to know. Implicitly, let me just finish. The teacher knowing the right hypothesis and the learner doing inference is sort of buried inside here, right? In some sense, you might say, well, there's a goal, right? The teacher has a hypothesis, that's the goal here. But all of the goals are identified with hypotheses. And so it sort of drops out, right? You don't have to sort of worry about it explicitly. And that's a sort of interesting feature of the setup. Yeah.
So I noticed that you call this optimal transport problem, but by using KL divergence, why not using the Watson-Stein distance?
So let's see. Right here, when I showed this formulation, this is the sinkhorn divergence, right? And so that's exactly it. And so basically, it's a bit of mathematical obfuscation, right? So the KL terms here, this one in particular, is you can think of as entropy, right? So that's exactly what's going on there. And then this term is going to be like the product between cost and plan, right? And so implicitly, that's exactly what we're doing is an approximation of that plus some extra stuff. Yeah. Right. Any other questions? Right. And in particular, when epsilon goes to 0, you get back exactly optimal transport, right? Wasserstein distance, assuming there's a metric on the downstairs, et cetera. All right. So I want to argue that this all collapses back down to the sort of more traditional stories, right? We've done a proper generalization of prior models in order to get here. And so we can take a look at this minimization problem, which again is the product between a cost and a plan with an entropic regularization term. This is what we were doing in that first recursive calculation. Secretly, that recursive calculation is exactly sinkhorn scaling, which I didn't say, but is true. And so it's optimizing the dual of this formulation right here. We can re-express this with a KL term instead of an entropic term by looking at the independent coupling. And so again, here we're thinking about discrete and finite sets, so everything is sort of simpler, less mathematically general. And the bit that I would like to highlight is that these terms all map, right? In particular, this term arises when we think of costs as being negative log probabilities. And so this is exactly going to be a cost. And here's our plan that we're optimizing. And so the reason why this term doesn't appear up here is because by assumption, we already know the correct marginals, right? So we assume that we have that shared common ground. All right. So to complete the story, some people have already seen this if you were here the first week. This whole problem of formulating cooperative communication with perfect common ground is exactly entropic optimal transport, which can be solved via sinkhorn scaling. It's the dual of the problem. And this has a nice mapping down onto probabilistic agents reasoning about each other, like the story I told at the beginning. Moreover, we can actually parameterize the host of existing theories. This comes out as a little bit small, so maybe I'll just blow it up so people can see. There are many theories that people have proposed: Jerry Zhu's machine teaching in the machine learning literature, naive utility calculus in cognitive development, rational speech act theory in linguistic pragmatics, value alignment in more robotics-y settings. These all vary along two interesting dimensions. One, sorry, I've changed my notation here, but choice of parameter, so your entropic regularization parameter is either going to be something like you want an optimal plan, like a Wasserstein distance, or you want to fit it based on the data, or you assume it's 1, in which case you have something like probabilistic selection. So people vary along this dimension. They also vary in how they use sinkhorn scaling. So the original way in which people set up this problem was more like this, right? Probabilistic agents reasoning about each other. And in particular, what you do is you sort of think about the Bayesian agent starting out, and then you say, well, we'll do one step. So a teacher's just going to reason about a Bayesian agent. And then that's going to be the data they produce, one step of that. And what I described is actually recursively reasoning all the way, because that's actually what gives you the equivalence in relation to optimal transport. We can also debate whether it's a better model of the empirical data, but I don't want to get bogged down there. Except to say that clearly, if you're doing one step of this recursion, you're doing an interesting form of approximation. And we can be a little bit more precise about how that's working through a variety of methods that exist in the literature. But the basic idea being, your number of steps of recursion is a method of approximating an optimal transport plan. And so people differ on that dimension in terms of what they propose. Now, all these models existed. Nobody compared them to each other. There was just never any clear reason to do so or rubric for doing so. But I think what this suggests is that they're all very naturally thought about as different approximations of optimal plans, optimal communication plans. Again, in the case where you have perfect common ground. And so we can sort of, what I'm trying to argue here is that we're going from empirically grounded things that people used in experiments of various kinds up to models, and then up to mathematics, and then generalizing again to the authentic problem that we actually face, which is that we don't know what each other knows. I'm going to skip past this, but the basic payoff here is that reasoning at this level, you have math on your side. Down here, it's very, very unclear. You have to basically go through the iterations to get predictions. Whereas up here, we know a lot about optimal transport, 200 years, and so you can leverage that. And that carries over to the setting where we're thinking, which is slightly more general than optimal transport. It's actually unbalanced optimal transport, but yeah.
Can the teacher be somewhat noisy and make errors sometimes, or is it assumed that it's always 100%?
Yeah. So that's this parameter right here. It's the softmax parameter that you know and love. And so, or sort of like it anyway. I should be a little careful here. It's very much like the softmax parameter that you know and love. And so if you have it at 1, then you have a stochastic teacher under most circumstances. And if you have it, going to 0, then you get back a deterministic optimal transport plan.
And would the interlocutor make any inferences of the reliability or accuracy of the teacher? Is there any notion of similar to trust, for instance?
Yes. So this is a great question. There's sort of 2 ways one might think about this. Well, there's many ways, but I'll give you 2, and you can come up with your own. One is you might try to fit that parameter. Now you're in the world of non-convex problems, and so life is a little bit harder, but that's an interesting question. We actually know a fair amount about these objects. Entropic optimal transport plans have some really nice geometry underlying them, and so there's beautiful results there that you can leverage. But it's still tricky to fit those parameters. The more general thing is you might authentically want to be like, well, maybe this person is telling me an untruth, right? They believe X, but they're trying to convince me of Y. And you can do that also. Perhaps, obviously, the scaling becomes the real issue and impediment there, right? Because now you're thinking of all of the hypotheses that you could have, cross all of the hypotheses that you could be being fooled about, and then the data in there, right? And so you can start to think about exactly these kinds of things. But that side of the world is much less developed.
Is there any crossbreed with active learning here, or different kinds of uncertainty that one might observe?
Yeah. That's a really interesting question. So this doesn't wind up being exactly active learning, and there's an intuitive explanation, right? In active learning, you don't know the answer, so you marginalize. In teaching, you do know the answer, so you don't marginalize, right? And so that's the reason why they don't sort of line up exactly. That said, there is an interesting story to be told here about how this relates to learning in general. And in particular, right, what you're thinking about when you're getting a coupling is basically a reversible plan, right? And that's why it's a good communication plan, because teacher's going to generate data and learner tries to invert the process. Now you can try to do that to yourself, right? So you choose interventions that are interpretable, explainable somehow. And you get a story that's not quite active learning. It's, I don't quite know how to call it, but it winds up being pretty interesting. And we have some papers on ways to think about that too, which I can point you to. NeurIPS last year or the year before, I think. Generalized belief transport, and I can email you the paper. Right, so we have math on our side. We can do things like, here's just a statement of continuity, pretty boring, but fine. There's many, many other things you can do, right? Optimal transport is a very, very active area of theory, multiple fields metals this century, also 200 years of work. And as everyone knows, very prevalent in machine learning these days. Okay, so by way of wrapping up, what I was trying to argue is that we can start to think about scaling up these experiments, right? We can bridge over to the world of machine learning and AI and make use of the tools, and those tools are understandable in the context of the way we think about human agents. And so, whether these ideas matter, I think is yet to be determined, but they are interpretable, and I think that's promising. On the other side, I think it's a little bit less clear because we're behind the times a little bit, right? Variational autoencoders are cool, and they're definitely interesting machine learning methods, but they are not the state of the art in language modeling right now. That would be transformer architectures, and so I think there's further ways to go in terms of understanding, and I think it's an open question as to whether we can exactly understand the things that we thought about in human communication as existing AI models, or whether there should be modifications somewhere in order to make them align better somehow with our intuitions about how communication works, not just predicting next tokens consistently. But I think that's the interesting work here, right? I think that's the fun question is, if it winds up being exactly equivalent, then hooray, we've got something, some new way to, I think, interpret and think about, useful in the sense of thinking about how humans interact communicatively, and also how language models might do so. And if they're not quite equivalent, then it might suggest ways in which we might extend the theory and opportunities to produce more functional models. Functional in the sense of not necessarily producing next token statistics, but in terms of producing useful communication to humans, which need not be exactly the same. So I have ideas about the transformer thing. I'm mostly out of time, so I'll skip past them. But I want to end with this sort of very, very big aspiration, right? Like, the way we communicate is magic, right? Like, it really is. And it's super central to the way we think about the world, right? You're all sitting here listening to me tell you about my experiences so that you may know what I've experienced, right? And we do this all the time, right? We're in a university where we pull people out of the environment to learn about biology, for example, right? And it's a testament to the power of human communication that makes any sense at all. And this question of common ground is just fundamental, right? We just never quite know what each other knows. But nevertheless, nearly everyone learns a language and communicates successfully with other people in their communities. This is not like learning to read, right? Communication is nearly universal. And so if we really want to understand how we get new ideas, how we build new ideas and things like this, and how we might have machines that help us do the same, I think this is important to understand. And I think we all are here because there have been great advances in deep learning, language models being just one example. And I think coming to grips with, what are the theoretical understandings that we should have to understand when we can use them effectively, but also how we might make them better, right? These are very interesting and open questions, and so that's sort of what we're going for. So I should thank people that gave us money. This was, as one must, DARPA funded a bunch of this work at various times. Not anymore because I'm there, right? Like, that's not allowed. As well as a variety of other organizations. I'll say that this is Yash. Well, you'll all be here, but he'll be at Machine Learning Symposium at New York Academy of Sciences, but he has a great paper that will be at NeurIPS on reinforcement learning in continuous time, distributional reinforcement learning. So we'll be there talking about that. Here's Xiaoran. He's gone off into the world and is doing other great things. And Pei and Jesse are two other former postdocs who did the work, the original work on relating to optimal transport, the basic formulation. All right, so thank you.